Hi, everybody, and welcome to a review for AP Physics 2. Today, we'll be talking about topic 6.5, image formation with lenses and mirrors. Now, you've heard us say a few times, for the first few days, we're going to be presenting content from the end of the course, even if it's not necessarily going to be on the exam. By the end of next week, we'll have a schedule posted about the other topics that we'll be teaching so you can customize the review just for you and decide on the sessions that you want to take with us. A quick rundown of today's lesson. We're going to start with a lesson overview and then go through our daily warm-up, that question that we do every day. We'll pick up right where we left off yesterday. Then we'll talk about what you need to know about image formation with lenses and mirrors. Then we'll work through some guided practice problems, questions that you may have seen in the AP Physics question bank. Then we'll work on a debrief and summary, talk about what we learned today and the questions you should be able to answer. And then finally, we'll leave you with an AP exam practice question. So I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas. Let's go over a brief lesson overview of what we'll be talking about today. We'll start with images in a plane mirror and how we perceive our own reflection.
And then we'll talk about thin lenses, the difference between convex lenses and concave lenses. We'll talk about the anatomy of a lens, really. It's the focal length, the radius of curvature, and the different types of lenses.
And then we'll talk about the image formation by these thin lenses, by focusing and projecting real images, how you can view virtual images. We'll do a little bit of math with the thin lens equation, and also talk about magnification.
So here are some things we think you already know going into today's lesson. I think that you remember that light bends as it passes from one medium into another. I think that you know that light slows down when it travels into a more optically dense medium, when light travels from a medium with low index of refraction into a medium with high index of refraction. It slows down. And the skills that you'll need to work on today are using representations and models to solve problems and also using some math. So I hope you brought along your trusty calculator.
And by the end of the lesson today, we hope that you'll understand what type of image forms from which type of lens.
Sounds great. So let's get started with some warm-up questions. First of all, after yesterday's lesson, I bet you can answer this one. Which of these three figures correctly shows the path that a light beam would take as it travels from air through a solid glass object and then back into air? The image on the left shows a triangular prism. The image in the middle shows this sort of round glass shape. And the image on the right shows a glass sphere. So think about whether light bends towards or away from the normal as it passes from air to glass and then from glass to air. Only one of these images shows the right behavior for light. That central image, the one that you'll learn soon is called a convex lens. That's the one that shows the right behavior for light at each boundary. So here's the question that we left you with yesterday. There was an air bubble in water, and approaching that air bubble were two light rays, and your job was to sketch the paths of light ray A and light ray B. So we're going to start by talking about light ray B, probably the easier of the two. You may recall Snell's law, n1 sine theta 1 equals n2 sine theta 2. Well, here's the thing. If theta is 90 anyway, if the if theta is 0 and the ray is striking that interface layer perpendicular to the layer, there is no refraction, there is no bending. The light ray will move faster in air, but it won't move at a different angle. So the same reasoning goes for the rest of ray B. Now for ray A, we need to think about how ray A is lined up compared to a normal line drawn perpendicular to that air-water interface. The angle of incidence is marked there as theta I, and our job is to estimate the angle of refraction. Well, as light travels from an optically dense medium into a less optically dense medium, from water into air, that light ray bends away from the normal. So that's how I sketch it. If you sketched it at some angle above flat, good for you. At the second interface, where the light ray passes from air into the water, we have to again consider a line drawn normal to the interface. Look at what the incident angle is and think, what might the refracted angle be? Well, as light passes from a less dense material to a more optically dense material, from a low N to a higher N, it bends towards the normal. So if your sketch looks something like that, that's fantastic. Good for you.
So what you need to know today, you need to know the law of reflection. You need to know virtual images and real images, lens types and characteristics of those lens types like convex, concave, radius of curvature for those lenses and the shape, the focal length and the radius of curvature. We'll also talk about image formation, using a ray tracing diagram to locate the image, and also using the math to also prove where that image should actually show up. And you'll also need to know the very last topic for today, which would be magnification. So we'll start with the law of reflection. Law of reflection is pretty basic. It says that when a ray of light hits something that's shiny and reflective, as long as that object is flat, when the light ray strikes that surface, it's going to bounce off at the exact same angle. And that angle is actually measured normal to the surface. So as you see in the diagram, the theta I, which is on your left-hand side, that's the incident angle measured to the normal line. That's going to be the same as the refractive angle on the right-hand side. So law of reflection just says the incident angle has to be the same thing as the refracted angle. The most familiar thing that you know of that's a plane mirror is a mirror, right? You have a mirror probably in your restroom or on a door, or maybe even in your car. You have a plane mirror, and those are typically flat and they have a reflective surface, but they have a couple of behaviors that are very interesting.
Plane mirrors can do a trick. They form images. And the only way you can see anything is that light rays bouncing off of everything around you, they enter your eyes. When you look at a mirror, everything that you see in that mirror is being reflected off the surface of a mirror into your eyes. Except that our primitive eyes aren't really good at understanding that light can be reflected. We're very convinced that light rays travel in straight lines that don't bounce off of stuff. We are convinced that the light rays come from behind the mirror. Now, you have experience with mirrors. You've seen them before. You know what they're about. This is what really happens. Neither of us are great artists. That's a decent stick figure. Light rays coming from the environment bounce off of someone. In this image, I've only drawn 2 light rays, one coming off the person's feet and one bouncing off the person's head. We'll talk later about how light rays really are essentially infinite in number. There are many, we just draw the special ones. So notice light rays bounce off a person's feet and off of their head, and someone else is looking at the reflection of that person. In both cases, the angle of incidence equals the angle of reflection, just like the law of reflection says. That's what happens. However, when we interpret that image, it's something else.
So when you are interpreting that image, your brain actually thinks that that image is on the other side of the mirror. You can actually test this by standing in front of a plane mirror and holding up what you know is your right hand And inside of that mirror, what does it look like? Which hand are you actually raising? Mr. Mancino, what happens there?
Right hand, left. I think my video is flipped for the students. I do know my right from my left. What you'll also notice, if you look in a plane mirror, if you can focus on a speck of dust right in the mirror, and then focus on your own reflection, you'll feel your eyes focus on a point further away than the speck of dust. Even though you're only still looking at the mirror, you're looking further away. The image that's formed in your brain, your interpretation of what you see, your perception of what you're sensing is on the opposite side of the mirror. Now, it looks to be the same size as the object and the same distance away from the mirror as the object. An image formed like that has a special name in physics. It's called a virtual image. We perceive a virtual image when our eyes sense light rays spreading out after reflecting off of a mirror or refracting through a lens. The light rays that form a virtual image, they don't actually originate where they appear to come from. There's no person on the other side of the mirror. Now, you know that now. You're a smart AP physics student. However, even though we eventually learn how to interact with our senses, babies take some time to get it right. When a baby sees a mirror, they think they have a brand new best friend. Also, cats. So I added a lot of pictures of cats to this. That's probably something you should know about me. An image that we had on yesterday was this one, an image of water in a wine glass. And I said we would come back to why the water seems to flip the image over and why it's in focus while the background is not. Refracted light, that's light bent through a material. Light that follows the law of refraction, that follows Snell's law, can be used to form images. We'll talk a little bit later about ray diagrams, tracing light as it travels before hitting a lens and then after going through a lens. They can show how and where images of objects are formed. Now, the geometry of a lens, its shape, its thickness, determines where the image is relative to the object. We'll discuss what that means. And we'll use ray diagrams to determine the size of the resulting image, its magnification compared to the original object.
We'll also come to find out that lenses refract light in a very organized way. And in AP, we only talk about double spherical lenses or biconcave, biconvex lenses, in which both sides of the lens have the same radius of curvature. And let's talk a little bit about radius of curvature.
Yeah, you mentioned radii and spherical lenses. We really do just mean the word radius in the same sense that you know it perhaps from geometry class. So here are two circles that overlap a biconvex lens. A double spherical lens is a lens that bulges in the middle and is thin on the edges and really is the shape of a thin slice of the place where two spheres would overlap. I know it's difficult to think of spheres overlapping in three-dimensional space, but if you have really good spatial reasoning, you might be able to imagine two spheres merging together, and the place where they overlap is where that lens is. The radius of curvature really is just the radius of one of the circles. Here is an image of a lens with a small radius of curvature, and here's one that's just as tall with a medium radius of curvature. And here's one also just as tall with a long radius of curvature. And you might notice that the radius of curvature affects the bulginess of the lens. Now, convex lenses have that characteristic shape. They bulge outward. And bulging outward affects the way that they interact with incoming light. So if on this convex lens, this bulging outward lens, we send in some parallel rays from the left side of your screen, when those rays strike the lens, they follow Snell's law. They follow the law of refraction. They bend towards a normal line. But then they refract out the opposite side of the lens. So if you look at the path that that light makes, you'll notice that when it leaves the lens, those light rays converge on one central focus point. And this is the behavior of light passing through any convex lens. You may have seen it in projectors, in cameras. There's another LCD projector. Mr. Eaton, let's hear about these images.
So an image that can be projected onto a screen, something that you can actually use with like a projector, is called a real image. And actual light rays are meeting at a certain point to form the image. I think we just saw a diagram that showed where these light rays are converging, aka meeting at a point to form an image. And we see it again here with the light rays on the left-hand side are traveling parallel to each other. And as soon as they hit that lens, they're refracting according to Snell's law and meeting up to on the right-hand side to form what we call an image. It's called converging when they all meet.
So here's an image of that actually happening with an actual lens. I didn't just want to leave you with a diagram, and I can't do this with Jello. I don't have that many lasers here. So I told you that we would talk a little bit about the properties of lenses, the characteristics of lenses, and a main characteristic is something called the focal length of a lens. The focal length of a lens is 1/2 the radius of the lens. There's some important things that lenses do at their focal points, which are one focal length away from the lens. So in this image, you saw how the light rays converge at one point. That point for incoming parallel light is called the focal point. You can see here light is converging at a focal point. Those focal points are on either side of the lens, and in this course, we only use what are called spherical biconvex lenses that are uniform, so focal points line up. For a convex lens like this, you have the two focal lengths, and it behaves in a certain predictable way. So that is a convex lens. Mr. Eaton, let's hear about the other sort.
Yeah, we can contrast that to concave lenses. And I think of it as both sides are caved in. And what these lenses do is they actually diverge light instead of converging light. Diverging just means that it's spreading the light out instead of focusing it on one single point on the other side of the lens. So the interesting thing about this, though, is with our convex lenses, we could form virtual images. And with this one, we can also still form virtual images. And I think we've got a slide that shows, yeah. So there's your light rays coming in. They're all parallel to each other and happy. They hit the lens, and again, they still have to follow the law of refraction. And as they pass through the lens causes the light rays to diverge away from each other, as you see on the right-hand side. So it kind of looks like I'm not going to get an image on the right-hand side, because we knew from the biconvex lenses that where the light rays converge is where we see an image. So I wonder what's going to happen in this situation. And you can still see with lasers here that, you know, it really does happen. We're not just lying to you.
All right, so here come the rules for image formation with a convex lens. So we're going to teach you 3 rules for drawing the path of light as it moves through a convex lens. Now, there are infinite light rays that you could draw, and each one would follow Snell's law. These 3 specific rays are just the really easy ones to draw. Rule number 1, rays parallel to the principal axis. Rays that strike the lens parallel to the principal axis refract through the focus. Rule number 2, rays through the center of the lens are not refracted. They leave at the same angle at which they came in. Rule number 3 is that rays that travel through one focal point before they hit the lens leave the lens parallel to the principal axis.
I think they should write this down.
I think they should definitely write those down or take a
Or
screenshot.
take a picture.
Didn't bring a notebook. Screenshot that? Okay, good. So here we have your very first ray diagram. I'm excited too. On the left, we see an object represented by an arrow. In the center, we see a convex lens with both of its focal points marked. And down the middle, that white line is what we call the principal axis. Mr. Eden, can you take us through how these rules apply to this situation?
I would love to. I think a common misconception is where the light is typically emitted from. And I like to tell my students, let's just pretend like it's a torch, right? And there's just a little fire at the very top of the object, and that's where the light is being emitted from. And again, we're just using these diagrams to estimate where the image is going to show up on the other side of the lens. So in order to draw a ray diagram to predict where that image will be, you start by drawing a ray from the top of the object parallel to the principal axis. And just to review something really quick, the principal axis is that white line that's pretty much drawn normal to the center of that lens. So that first ray leaves the object parallel to the principal axis, strikes the lens, and bends downwards through the opposite focal point, as you see labeled F prime. The second ray that we need to draw is the ray that travels through the center of the lens. Now, rays that travel through the center of the lens do not refract. They just keep on trucking all the way over to where we meet with the first ray that you drew. We'll give you a second to draw that. And the third ray, third and final. This guy is going to leave the top of the object, travel down through the first focal point, strike the lens, then travel parallel to the principal axis. It's essentially just the opposite of the very first ray that you drew.
So on the right side of your screen, you see another arrow labeled image. If this lens were being used to project an image of that object, where you've drawn the second arrow is where that image would be projected in focus. So now we have a few examples of lenses focusing images of an object at different locations from the lens. We'll talk about what changes in the image based on the object distance. In the first example, the object is pretty far from the lens. It's more than one radius of curvature from the lens. So rule number 1, in parallel out through the focus. Rule number 2, through the center is unrefracted. Rule number 3, through the focus out parallel. Now those lines all meet up at one point. We would be projecting a flipped upside down and inverted, reduced, smaller image. It's projectable, so it's real. So it's inverted, reduced, and real. Mr. Eden?
All right, the second image or second object that we'll deal with looks like it's at 2F. Correct me if I'm wrong, Mr. Mancino.
I believe it is a little bit further than 2F.
Okay, we are not at 2F yet. Okay, same thing as before. You start parallel to the axis, down through the focal. Straight through the middle, and down through the focus, then parallel. And the image that you see on the right-hand side is still a little bit smaller than the object, and it's also inverted.
In the third example, the object is even closer. The object is just behind the focal length of the lens, just further than 1F away. Same 3 rules apply. Except this time you'll notice that the image is huge. This is how a projector works. A very bright object, a very bright LCD screen with a light behind it, shines through a lens, and that lens projects a very big image very far away. So converging lenses can form real images, projectable images like that, but they can also form virtual images. That's what happens when you use a converging lens like a magnifying glass, like that, or like that. So in this example, the object is closer than one focal length. It's pretty close to that lens. Think about when you use a magnifying glass, you hold the magnifying glass close to the thing that you're magnifying. The same rules apply. It's easy to draw the first two rays. Explaining the third one would take more time than we have for this video. So we're just going to draw the first two rays, and this part is strange. See, the observer of this image would be somewhere on the right side of your screen. And you'll notice that the rays that go to the right side of your screen are spreading out. They are diverging. So if your eye were over there on the bottom right side of your screen, your eye would think that top ray came from somewhere over there. Your eye would think the bottom ray came from somewhere over there. And your eye would say, now wait a minute, there must be something really big over there. So here's what an AP Physics question about that topic might look like. An object is placed in front of a converging lens at a distance from the center of the lens equal to half the focal length. The object distance is smaller than a focal length. What kind of image would it make? Now, we just saw this, and I think you'll notice very quickly the options are, is it upright or inverted? Is the image larger, smaller, or the same? Your job as a smart AP Physics student is to say, wait a minute, that's a magnifying glass. Mr. Eaton, why don't you take us through how the eye perceives an image as it looks through a magnifying glass?
I would love to. All right, so just like we've done before, we can still trace these rays as they pass through the lens by starting off parallel down through focus and drawing that line that goes straight through the center of the lens and doesn't refract. Now, in order to figure out where that image is formed, we trace backwards after the refraction. And over on the left-hand side, you'll see where these kind of, notice that they're smaller dotted lines. The reason that they're smaller dotted lines is because this is where we're forming a virtual image. And that image is going to form back behind the object. Looks like it's larger and it looks like it's upright.
Now, I always get confused about the idea of lenses forming images. That always bothered me as a physics student. See, I could draw them, I could do the diagram, I could do the math, but what I never thought about was that it's not the lens making the image. It's us. So viewing that image, looking through that magnifying glass, is someone's eye. So on your screen is a sort of a two-dimensional side view of someone's eye. And like I said, there are an infinite number of rays shining off of the object and passing through the lens and following Snell's law, refracting according to Snell's law. I've drawn more of those rays, not an infinite number, but a lot of them. Now, inside of that eyeball, there's another lens that focuses the light at a focal point and projects an image. That image that's focused on the back of your eye depends on your perception of how light travels. If you're receiving those rays, your brain says, I know where those came from. They came from over there. So there's the biology of the sensation in your eye, passes through your optic nerve, and you process it. See, we've been saying that lenses form images, but the actual story is a lot more complex. Your biology, your expectations, and your experience combine to form the image. When similar rays of light strike different places on the back of your eye, you use that information to interpret where those rays came from. Mr. Eaton, I saved this one for you. The object is at the focal length.
This is my favorite. I don't know why. So if we notice on this one, we can still use all the same rules that we've talked about so far. Light leaves the object parallel down through focus. Light leaves object, goes through center of lens, keeps on going. But here's the problem. Notice on the right-hand side of the lens, both of those refracted rays are perfectly parallel to each other. So even if we tried to trace them backwards to the same side of the lens where the object is, as in the previous example, they will never converge. So in this case, when the object is at the focal point, no image is formed.
So the image formation rules are similar for a concave lens, but flipped. Rays that enter perpendicular to the principal axis refract as if they came from the focus. Rays through the center are not refracted. And those two rules are enough to show us where the light rays would cross, where our perception of their crossing would be. You may want to take a screenshot of that one too. Speaking of things to screenshot, grab that one. This is called the thin lens equation. It tells you how the geometry of a lens, that's its focal length, can relate the image location, that's SI, to the object location, that's SO. The combination of object location and focal length determine where the image will be. So there are some important things to note in that slide. We're not going to go through all of the math right now, but the next couple slides are things that are quite important.
All right, so just a quick review and organizing what we've talked about so far. Convex lenses, so the ones that are biconvex, they form a real image if SO is less or greater than the focal point. They form a virtual image if the object distance is less than the focal point, and the F's are going to be positive. Whereas with concave lenses, we get virtual images and F's are negative. The focal points are negative on concave lenses. So a couple more things here. Virtual images are produced by diverging light rays, and the image distance is going to be negative. Whereas with real images, we have converging light rays. Remember, light rays are coming together to actually form an image, and the image distance is going to be positive. So the second descriptor, or actually third descriptor in this case that we like to use, is talking about whether or not the image is going to be upright or inverted. So with upright images are always virtual. And the height of the image is going to be positive, because that kind of makes sense. If we're talking about that principal axis and the object is standing on top of the principal axis, that height's going to be positive. Now, when we have inverted images, those are always going to be real. And if we're going underneath that principal axis, that's usually a negative distance on a graph. So our height is going to be negative. And we have a practice problem for you. Example problem, I guess. Okay, an object is placed 32 centimeters from a converging lens with a 25 centimeter focal length. Where is the image? We need to start with the thin lens equation. So 1 over distance of the image plus 1 over distance of the object has to equal 1 over the focal point. So in this case, we're trying to solve for SI. That's the image distance. So just some quick algebra, I just moved 1 over SO to the right-hand side of that equation. Once we get to that point, we can go ahead and plug in the focal length, which is 0.25. Remember, that needs to be in meters. And we also plug in the object distance, which is 0.32. So putting that in the calculator, as you see it on the screen, gives you 1 over SI, which is the distance to the image, is equal to 0.875. Now, to get the final answer, we need to take the inverse of both sides of that equation, and that gives us a distance to the image of 1.1 meters.
Now, I need to jump in and apologize here because that one's on me. I wrote DI instead of SI.
Oh, yeah.
SI is how you'll find it on the AP Physics 2 equation sheet, and DI was how my old physics teacher in high school used it. So Mrs. Shear, thank you. And everyone else, I'm sorry.
Mine did the same. It's okay.
Next up, we quickly define the term magnification. Magnification is simply the ratio of the image height to the object height. If the image is 5 times bigger, well, the magnification is 5. Magnification is also negative SI divided by SO. There's a similar triangles proof that we're totally not doing here, but it's really fun.
All right, let's go over another practice question. A 2.3 centimeter tall object is placed 12 centimeters from a convex lens with a focal length of 36 centimeters. Let you digest that for just a second. So focal length is 36 centimeters. And it looks like the object
is only 12 centimeters.
Yeah, the object is what, 12 centimeters from the lens. So that's inside the focal point. And you probably remember what type of image was formed if it's inside of the focal point. Mr. Mancino, what kind of image is formed?
Inside the, well, I feel like it's a clue that there's a magnifying glass on the bottom of the screen. So here's going to be my suggestion. The next few slides, they're an example problem that you may want to work on your own. So I've left the solutions on the screen. As I click through, you'll see which solution goes to which part of the problem, A, B, C, or D. We're not going to spend a ton of time on it, but you can do it on your own. So there's question A and the solution to question A.
Virtual.
It was virtual. Part B and the solution to part B. Part C and the solution to part C. Is not showing up. Interesting. The magnification is 1.5. Part D and the solution to part D. The height of the image is 3.45 centimeters. So here are some common questions that you may see on a high school test, or if you're taking this for university credit, if you have that option. These are the sort of questions that we sneaky physics teachers like to ask you about lenses. What happens to the focal length if the radius of curvature is changed? What happens to the index of refraction, or what happens if the index of refraction is changed? What happens if we dunk a lens into a fluid that has a different index of refraction from air? In all of these situations, the basic thing to ask is what happens to the angle of refraction when the light passes into the lens? Going back to Snell's law will always get you where you need to go. Anything that increases the angle of refraction produces a shorter focal length as the light is bent a greater amount. So remember, as light passes from one material to another, it bends, and this occurs only if the two materials have different end values, and the greater the difference, the more bending there will be. Now that should seem familiar from yesterday. So I think everyone should be able to see a blue screen with a lens on it. You'll notice that this lens is quite thin right now, but I can change the radius of curvature of the lens. On the left side of your screen is an object, it's a pencil. On the right side of your screen is the projected image of that object. If I use a lens with a wider radius of curvature, it pushes the focal point way out, the lens is thinner. A shorter radius of curvature produces a wider lens. Raising the refraction index, raising the index of refraction for the lens, shortens the focal length, decreasing the amount of bending, decreasing the relative difference in the end values, increases the focal length of that lens. I'm going to go back to our presentation. All right. Mr. Eden, take us through the practice.
Sounds great. Okay, today we're going to try to answer 3 different questions. The first question that we have for you is determining the focal point of a converging lens The second question addresses graphing techniques to find the focal point of a lens. And the third is about the relationship between object distance and image distance. So let's see our first question. It's a little
That
wordy,
is a
but
lot of words, first of all. I know that's what my students are thinking. Help us parse this out.
all right. So it basically just says that a student has a laser, he shines it into the lens, he gets two traced rays on the other side of the lens. Let's see here, project the principal axis. Okay, he's trying to find the focal point of the lens. But the problem is the lens is actually causing the rays to diverge, so the student can't find a point where they cross. That's the next to last sentence there. Okay, which of the following changes to the student's procedure is most likely to improve the results of the procedure? You may recall previously we talked about lenses that diverge light. If the light is diverging, you can't figure out where the image is because the actual rays don't combine back up to form an image. We actually have to just trace them backwards. So the answer choices here, it looks like ACE has changed the direction of the laser. No good. Move the laser closer to the lens and repeat. No, I don't like that either, because that changes your object distance. Move the laser so that it has the same distance, but on the opposite side of the lens. No, that just completely changes everything. Option D says no additional data is needed. All he needs to do is extend the rays to the laser side of the lens to find the intersection point. And that's what we did in pretty much all of our diagrams for lenses that had diverging rays. So answer choice D is the correct answer.
In the next question, it's about a student they're focusing an image of an object and moving the screen to different distances to observe the focused images. Which of the following is the focal length of the lens? So for this, we need to think about the thin lens equation. 1 over SI plus 1 over SO equals 1 over F. So in the interest of time, we're going to continue moving, but knowing how to graph that relationship is really important if you're going to do a lens lab. When you get back to school, and I'm still saying when, I hope you get a chance to do this lab to determine the focal length of a lens. It's a blast, and you will find the inverse of the intercept of that line with the vertical axis gets you the focal length of the lens.
Okay, our last question is just a lens with an object and a very small inverted image on the right-hand side. And it says, how will the height of the image change if the object is moved to the left toward the position of the dot? It's not saying that the dot is the focal point, it's just saying it's going to move the object to the left. Now you'll recall from the diagrams that we showed you before, as you move that image further away, the first refracted ray, the one that you draw parallel and down through the focal point, is going to bend up just a little bit more. So in this case, the height of the object will decrease.
Oh, you mean the height of the image will decrease?
The height of the image will decrease.
Yeah, the further away we move that object, the smaller the image will be. That second ray that passes through the center of the lens, unrefracted, is going to be at a shallower angle. All right, let's summarize and talk this through. First of all, here's what we were hoping that you're walking away with today. First off, the law of reflection states that the incident angle equals the reflected angle. Plane mirrors reflect light to form virtual images. Remember the babies looking through the mirrors at their new best friends? Lenses refract light to form images. Converging lenses can either project a real image on a screen, and they can also form virtual images when used as a magnifying glass. Diverging lenses can only form virtual images. And we're hoping you can graphically or mathematically determine the location of an image, either using the thin lens equation or using ray tracing.
We have a couple of things that we want to ask you. What is the lens equation? Do you remember? And what does it mean for the image distance to be negative or positive? How do you know about if an image is considered virtual or real? And why does light bend through a lens anyway?
So here's a couple of quick questions for AP practice. We're just going to leave you with these. We are not going to talk about the answers. The figure shows a converging glass lens in air. An object is to the left of it and a screen is to the right of it. The entire system is placed in a material which has an index of refraction slightly lower than that of air. That's a weird material. How will the focal length of this lens change and why? Finally, this is one you'll want to take a screenshot of. The figures below show a cross-section of a lens. On each figure, draw the ray as it passes through the lens and then enters the next material. On the left, that's a lens in air. On the right, that's a lens in water. So your first job is to basically do the backwards of what we did to start off class today. But then it's your job to describe how the focal length of that lens and the position and size of the image formed agree with what you drew. One of your tasks as an AP Physics student is doing something called a qualitative quantitative translation, where we talk about, in words and equations and drawings, the same phenomenon. In this case, it's image formation by a lens. We've talked about it in terms of the thin lens equation, in terms of diagrams, and in terms of, we're hoping right now, a narrative. So take a screenshot. The answer is coming tomorrow. Now, we know that not everyone has access to the internet, and we are working hard on solutions to get you what you need. If you or someone you know needs mobile tools, needs help getting connected, reach out directly to the College Board and let them know, cb.org/tech. I can promise you they will help you solve your problems on an individual person-by-person basis. If you want to take this exam, we're going to make it happen for you. So thank you very much for watching. Thanks for joining us. We hope you join us again on Monday. Be sure to complete the practice questions because we're going to start class with that next time.
All right. Thank you so much, everybody, for joining us.